Alright, so here's the second section. This one's all about gravitational field strength. So related to gravity, not the exact same thing. You'll see why. So gravitational field strength, today we're going to figure out what's the idea behind fields. You need field strength, you need to understand what a field is. We're going to learn gravitational field strength and then solve some questions involving this. And then we're going to see how gravitational field strength relates to satellites, because those are related to each other. So what is a field? Well, if we've got two objects that are not physically in contact, they can still exert a force on each other. So think gravity. Planets don't touch each other, but they're pulling each other. Or if I take two magnets and put them close together, they're going to interact without actually touching. Same with charged particles. Fields are describing a sphere of influence. So they're influencing other objects around it. So we say that it creates a field of influence, depending on the type of, it's either gravitational field, magnetic field, electrostatic field, something like that. So if we consider a campfire, we can imagine there being a heat field. There isn't technically something called a heat field, but we can imagine that. So here's the dude standing by a campfire. If he gets closer to the fire, he's going to experience a greater heat. Similarly, if the fire gets larger, he's also going to experience a greater heat. So we have this kind of a similar idea with gravity. If you get closer to an object with mass, you're going to experience a greater gravitational field. And if you increase the mass of a planet, you're going to experience a greater gravitational field as well. That's how you can kind of picture it with gravity and heat. You can kind of compare it between those two. So gravitational fields are defined as G equals, little g is gravitational field. It's the force of gravity divided by m2. Now m2 is the mass that is around the planet, or the secondary mass. Just to remember from last lesson, Fg is equal to g m1 m2 over r squared. So if I plug that equation of Fg into the equation for little g, I will get this equation. So notice it's the same as Fg, except one of the masses has disappeared. M1 is the mass that's going to create the field. So if asked for gravitational field strength caused by the Earth, I'd use the Earth mass. If I say what's the gravitational field caused by me, you'd use my mass. And the units for G are either newtons per kilogram, because it's Fg over m, or meters per second squared. And meters per second squared you should recognize. Gravitational field strength is also known as acceleration due to gravity, which we have learned about that back in kinematics. So for Earth, you actually know what the gravitational field strength is. It's just 9.8. So let's do some problems here. I've got the moon is in an orbital radius of 385,000 kilometers around the Earth. What is the Earth's gravitational field strength at this distance? So here's a picture of what's going on. We're told the distance from center to center is 385,000 kilometers. Here's our equation for our little g. And notice for this, it's asking what's the Earth's gravitational field strength. So even though you have on your formula sheet the mass of the moon, I don't need it, because all I care about is what is the Earth's mass. That's the only one we're looking at. So plug in the numbers. Notice here I converted kilometers into meters for the orbital radius. And we get a really teeny tiny number because it's a very small acceleration. So in the last question, we're shown, as I just stated, that the moon is actually accelerating towards the Earth. So why don't they actually collide? Well, if you think about it, so here's the Earth and the moon. Yes, there's a force of gravity between them, but the moon has inertia. It's orbiting around the Earth, so it actually has some speed, which causes it to rotate in a circle around. So even though that force of gravity is always pulling it towards the Earth, its speed, or its inertia, causes it to keep rotating around in a circle. So that's how satellites work. So that's acceleration due to gravity, or gravitational field strength. It's pretty straightforward. It's very similar to Newton's universal law of gravity, except now we're just taking out one of the masses. So you got to be careful in reading the question to see if I am asking for force of gravity or gravitational field strength, because if you use the wrong equation, you'll get the entire question wrong. So just be very careful in reading the question. Alright, so here's another kid edition physics movie video thingy. Hello, special guest.
Hello.
Okay, so for this one, different movie. This one's from the movie Up. You haven't seen this one yet. You haven't seen most of the videos we're going to do. That's okay. So it's going to be a surprise for stuff that's going to happen. I'm going to play it, and then you need to see if you can see what's not physically possible, okay?
Okay.
Okay, here we go. All right, kiddo, what do you think?
I think it can't be. The house is so heavy.
It's so heavy.
Yes, because I don't think it can fly that long.
Uh-huh. Yeah, you'd need a lot more balloons to be able to lift the house.
Yeah.
Even though, look at this, how many balloons are there? How many do you think?
So many.
So many. If you were to guess, how many balloons do you think that is? Oh, that's a lot. Like 1,000?
Yeah.
Or a million?
Or a million. Yeah.
Maybe?
Yeah.
I don't know. Maybe like a couple tens of thousands?
Yeah.
There's a lot. But do you think there's enough balloons there to lift the whole house?
I thought it would just like drop down right there.
Oh, yeah.
Like the car would like just fall down right away.
Mm-hmm. Yeah, with this one, there's not enough balloons to be able to lift the house. You'd need a lot more balloons. I don't think there's that many balloons available.
Yeah.
Is that a good one?
Yeah.
Yep. Okay, so that's what is not correct with this one.